about orders of different elements modulo prime number. And first of all, let's recall what is an order. If you have an element, you can keep raising it to higher and higher powers, and the order of this element would be the smallest power to which you should raise it to get 1. So last time we started talking about some properties of the order, and we proved some of the simple things. Example, if order of some element modulo p is k, then k divides p minus 1. So order of an element divides p minus 1. Another thing, well, we started counting how many elements of a given order are there modulo k. And the result is follows. Well, what we managed to prove. First of all, an obvious result. If the number k is not a divisor of p minus 1, there are just no elements of this order. It's the same statement, but we just repeat. If k does not divide p minus 1, there are no residues of order k modulo p. If the order does divide p minus 1, then we have several options. One of the options is, well, there are just no elements of this order. So if k does divide p minus 1, well, there would be no elements. As far as we know, there would be no elements of order k. But if there is at least one, and then a whose order is k. So if we manage to find at least one element whose order is k, then we actually know quite a lot. Then we can, for example, solve the equation x to the power k is equal to 1. We can write down all possible elements whose order is equal to k. So let me summarize this result. Then, one thing that we proved, equation x to the power k equal to 1 modulo p can be solved, well, has explicit, the solution for this equation is explicitly given by the following thing. Then x to the power k is equal to 1, if and only if x is one of the following. 1a up to a to k minus 1. So a raised to any power is a solution of this equation, and in fact, these are all the different solutions of this equation. There are k solutions here. Another thing that we proved, every element, all elements of order k are, well, here are all of them. They are all powers of a. I can restrict the powers between 0 and k minus 1. And if I want the order of this element to be equal exactly to k, then this 0, I and k should be equal to 1. So that's the result that we discussed last time. So once again, we know that order of any element is a divisor of p minus 1. If we fix some divisor of p minus 1, and we ask the question how many elements are there whose order is equal to k, well, we have two options. One option, there are just no elements of order k, well, could happen. But if you manage to find at least one, then you know all of them. Then all the rest are powers of the given one. Well, if you want the order of such thing to be equal exactly to k, you should have this power to be relatively prime to k. So once again, number of elements order k is 0 or 5k. It could be 0 actually. For example, if k is not a divisor of p minus 1, it's definitely 0. If k is divisor of p minus 1, well, as far as we know now, it could be 0, but if there is at least one element of order k, there are exactly 5k such elements. And here is a list of all of them. It's just there is exactly 5k numbers I which are relatively prime to k. The definition of 5 is. So what I want to prove today is the following fact. This option is attained only if k is not a divisor of p minus 1. So, in other words, if k is a divisor of p minus 1, then yes, there will be at least one element of order k. So, for every divisor of p minus 1, there will be at least one element of order k. In fact, there will be that many elements. So, to formulate the theorem, then for k which is the divisor of p minus 1, there are 5k elements of order k. So for now we know it's either this or there are just no elements of order k, and we want to prove that there is at least one element of this order, or there are exactly that many. So let me try to prove the theorem. By kind of in kind of funny way. So I know that if I want to count the number of elements of a given order, there will be either 0 of them or this amount of them, 5k. But you know, every element has some order. So if you just count the number of elements from 0 to n minus 1, well, you can group them according to their order. For each given order, you can count how many elements are there of this given order, and the sum of all these numbers should be exactly equal to n. So, beginning of proof. By the way, this theorem is kind of the first, I would say, really non-trivial theorem in our course. We actually started working on proving this theorem last time, and we'll finish today, and well, it's really a non-trivial result. Maybe it's actually the first result that in our course that needed actually Gauss to work with, not Fermat or Euler, but actually Gauss. So the beginning of the proof is like this. Let us take these numbers, the numbers from 0 to n minus 1, sorry, p minus 1, can be grouped according to their order. According to their order. So you get some kind of equality. That the number of elements which is p, so which is p minus 1, is, well, there is some amount of elements of order 1. What are they? Well, just the element 1 is order 1. So this is number of elements of order 1. Then you fix the divisor of, well, fix just some divisor of p minus 1, and you'll get some number of elements of this order. This will be either 0 or 5, this number. So then you'll have plus sum over k which divides p minus 1. K is not equal to 1. And here you will have some sums. It will be either 0 or 5k. Because we just showed that the number of elements of order k is either 0 or 5k. So this is number of elements order k. So somehow we should get this number p minus 1 using such a sum. And now a funny thing happens. It turns out that for actually any number, if you compute, so this sum, well, how large it is? It's definitely not smaller than 1. It's definitely not larger than the sum of 1 plus all possible divisors of p minus 1 of 5k. So it's somewhere in between. It turns out that even if you take all of the things here to be equal to 5k, not equal to 0, you'll get, well, exactly p minus 1. So this sum can never become larger than p minus 1. And if you want to actually achieve p minus 1, you'll have to make this choice, 5k here, at every step. So we will show any n for any n is actually equal to sum over its divisors of 5k. Here the divisors do include 1, so over all possible divisors from 1 to n. So in fact, if you compute this sum with making the choice of not 0, but rather the larger of the two choices, 5k, this whole sum will be exactly equal to p minus 1. So if at some place you decrease this sum, we choose 0 instead of this, you'll get a smaller answer. So, well, it means that this equality can hold only at each place the sum is actually equal to 5k. So this will show this. So, well, for the choice of n equal to p minus 1, we have in the sum p minus 1 is equal to sum over k which divides p minus 1 by 0 or 5k. All the choices must be 5k rather than 0.
What is 5, 1?
Well, 5, 1 is 1. And yes. So here we agree that 5, 1 becomes as 1. I think it's a reasonable convention because, well, if you know, if you take a number and write this n times 1, you do want to get this multiplicative property that 5 n is equal to 5 n times phi of 1, so phi of 1 should be taken from this middle case. Especially going here. So it's here and we're computing such a sum, it's the same here. Sorry? K equal to 1 is so that will be the argument. The only missing ingredient is this formula. So let's try to prove this formula. Or maybe before this, any questions about flow? For now, you should understand that if this formula is correct, then we actually prove the theory that there are exactly 5 k elements of order k for every divisor of p minus 1.
I have a question.
Mhm.
Before you said if k divides p minus 1, it's possible, maybe there is no elements for the
Yes.
k, but now like you're saying it's always
Yes. So
like always there
So
are
it looks,
elements.
works like this. I have my kind of residues modulo p, non-zero residues modulo p. I group them according to their orders. In each group, well, I know that there are all the elements will get divided to some groups. In each group, there are either 5k elements, so 5k1, 5k2, 5k3, or maybe 0. So some groups might be empty. But now, so somehow these p minus 1 elements get divided to several groups. But now, well, my claim is that it turns out that this number p minus 1 is exactly equal to the sum of the bigger choices of the sizes of these groups. So each one of these groups, well, it must contain exactly 5k elements. If one of them is smaller, then well, just there will be some elements which are still not covered.
Is it possible if k divides p minus 1, but there is no elements of order k?
Well, a priori it is possible. I mean, as far as we know, as we knew in the end of last lecture. But this identity shows that it's impossible. There will be exactly that many elements of order k. So that each group will be non-empty. Okay, other questions? So maybe let's try to prove this identity. It's a simple combinatorial identity that requires a slightly different combinatorial algorithm. So let's call it a lemma or no. Let's say that it's a lemma. So here we prove this identity. Once again, I'll interpret. I'll provide a combinatorial explanation for why it is true. So here how it goes. Let me consider all the numbers from 0 to n minus 1 and ask about each one of them the question: what is the greatest common divisor of this number and n? And let me group these numbers according to this greatest common divisor with n. And then I'll just count how many numbers have greatest common divisor of 1. How many numbers have greatest common divisor of 2. And so on and so on and so on. So the question is how many, so maybe like this, fix k which divides n. So I can write n is a multiple of k. K plus n. Question: how many x's between 0 and n have greatest common to 1, how many numbers have greatest common divisor with n which is equal to 1? It should be easy. 5n, yes. So for example, if k is equal to 1, then the number of elements whose greatest common divisor with n is equal to 1 is 5n. So now the question is, suppose that I want to find, suppose I pick some divisor of the number n, and I want to find out how many numbers have greatest common divisor with n, which is equal to that number. Well, it's not hard to cook such numbers. What do I mean? If every such number such x is of the form, well, definitely it should be divisible by k. It's k times some y. But of course, not every number of this form is good for my purposes. If I want the greatest common divisor of this number x and n, which is greatest common divisor of ky and k n, to be equal to k. So if I want this to be equal to k, well, both these numbers are already divisible by k. So it means that the other things, y and m, should be relatively prime. So this holds if and only if GCD y and m is equal to 1. Okay. So how many numbers are there of this form with y which is relatively prime to m? And y is, well, it should be smaller than m. So there are exactly 5 m such numbers. There are 5 m such numbers. Y between 0 and m, and then x is k times y between 0 and m. So the answer is, if I fix a divisor k of n, then the number of elements from 0 to n whose greatest common divisor is x is exact to k is, well, this number 5n. Conclusion. Well, let me take all the numbers from 0 to n. Well, each one of them has some greatest common divisor with the number n. It should be some divisor. So the number of elements n is, on the other hand, the same as the following sum. For each divisor of n, so for each way to factor n as a product of k and n, I will count how many elements are there of all which have common divisor k with n. And here's the answer, 5n. So this is great. So the thing is number of elements from elements x between 0 and n with GCD x n equal to k. But that's exactly this formula. Well, almost. So here I'm taking the sum over the divisors of n, but here I'm also taking the sum over divisors of n, except, well, my name is slightly different. Here, oh, it's actually the same, yes. If I have k which divides n, then, well, the other part, n divided by k, which is here denoted by n, also is a divisor of n. So it's the same sum, here and here. It's just kind of in the opposite order. In other words, here I can say that I'm taking the sum, well, not over divisors, but over all, say, factorizations of n as a product, taking sum. And then, well, it's just a matter of changing the names. Okay, so maybe we'll do an example because it's really a simple thing and I really don't want you to be confused. So, example. So if I want to prove something like this, that 6 is 5 1 plus 5 2 plus 5 3 plus 5 6, what I do is just as follows. I take the elements 0, 1, 2, 3, 4, 5, and that's it. For each one of them, I compute what is the GCD with GCD of this element with 6. Here I get so 6, 1, 2, 3, 2, 1. I count, so for each divisor of 6, I just count for each divisor of 6, I just count the number of elements whose GCD with 6 is equal to that number. So sum, okay, so here I have 5, 6 elements with GCD of this element with 6 equal to 1. Then I will have 3 elements with GCD of this element with 6 equal to 2. 2 elements with GCD of this element with 6 equal to 3. And what's that? 5 1 elements. So this last one is kind of formality. There is just one element whose GCD is 6 is equal to 6, and 5 1 is defined to be just 1. So it's so now if you want to count the sum of these numbers, well, it should be exactly 6. You just see that they are. Here they are. These elements are. These elements. These elements are. These elements. These elements are. These elements. And this is. So you see, you have just a partition of all the numbers from 0 to n into kind of baskets. Each basket has elements with a certain property. If you count the number of elements in each of the basket, in each basket you'll get this answer. And then you just say that the number of total number of elements each and the sum of elements in each basket. So maybe any questions about this? Okay, so well, so we have this identity. Once again, let me write it down. 5n is equal to, so n is sum of 5k divided by n. And in case that n is p minus 1 or p is a prime number, it has now a different kind of combinatorial name. If n is p minus 1, well, it has a combinatorial name of the following kind. Every element has some order, and the number of elements of order k is 5k. Has the meaning, and it can be interpreted. So we just prove this state. Because well, it's either this or 0, and well, it cannot be 0. Because every element should have some order, and the sum of such numbers is exactly p minus 1. So in particular, one of the kind of the most important corollaries out of this theorem is as follows: that there is at least one element whose order is exactly equal to p minus 1. The most important corollary in the primitive element theory there is at least one element whose order is p minus 1. Element majority. It is this fact for which we actually, well, it kind of summarizes everything that we did. This short statement that there is at least one element whose order is p minus 1 is, well, if you want to remember out of the last 3 hours just one statement, remember this statement. Let me explain you what it means. So in particular, what does it mean that its order is p minus 1? It means that all of its powers up to the power p minus 1 are just different numbers, are not equal to 1. So if A is such a number, such an element, and every B which is not equal to 0 modulo P is of the form A to the power I for a unique I between 0 and p minus 1. A to the power p minus 1 is already 1, but all the smaller powers are all distinct, and there are p minus 1 of them, so they should cover all possible elements. Such an element is usually called a primitive element. So, say that it's a definition. Such an element called a primitive element. So let me repeat. The primitive element modulo the prime number p is just some element whose order is p minus 1. In other words, it's such an element all of whose powers from the zeros to p minus second are distinct numbers. It's such an element such that every residue modulo p, which is not equal to 0, is some power of this number. Let's try an example. Let's find all primitive roots, all primitive elements modulo, say, 13. Well, unfortunately, there isn't a simple way to find such an element. I mean, we proved the theorem that yes, you can always find such an element. There is at least one. But to actually find it, well, you'll have to try a couple of different elements. and see whether each one of them is actually a primitive root or not. So let's try. One cannot be a primitive element. So one isn't a primitive element. Quite obvious. 1 to the power 1 is already 1. And so its order is equal to 1. With 2 it's more interesting. So try 2. What should we do? We should compute all the powers of 2 and see whether there is some small power such that raised to this power and get 1. Well, 2 to the power 1 is 2. It's not equal to 1. Even modulo 13. 2 squared is 4. It's not equal to 1. Modulo 13. 2 cubed is 8, still not equal to 1, modulo 13. 2 to the fourth is 16, which is 3, which is not equal to 1, modulo 13. Should we compute 2 to the fifth? Could it be equal to 1 modulo 13?
No, 5 already paid for.
Yes, exactly. So this is not equal to 1 modulo 13 because, well, order of element, order of 2, modulo 13 must divide 12, which is 13 minus 1. So a priori we already know that order must be a divisor of 12. It could be 2, could be 3, could be 4, could be 6, could be 12. But never 5. Well, 6, we should check. 2 to the power 6. First question is, how do we compute it? Here's one way. You can take this thing and square it. Another idea, take this thing and multiply by this thing. Both work, and I guess it's easier to multiply. So it's 2 to the fourth times 2 squared, which is 4 times 3, which is minus 1 modulo 13. So 2 to the power 6 is minus 1. Should we check? Should we compute anything else?
No, for the thing that we like 5.
Yes. So 2 to some power should be equal to 1. But this power, well, the smallest power, should be divisor of 12. And we already checked all the divisors of 12, but 12 itself. We know that 1 doesn't work, 2 doesn't work, 3 doesn't work, 4 doesn't work, 6 doesn't work. That's it. It means 2 to the power 12 is equal to 1, just as Fermat's little theorem. Or minus 1 squared is equal to 1. So 2 is a primitive element. 2 is a primitive element. Okay, so maybe any other primitive elements? Well, we know the answer. How many primitive elements are there? There are exactly 512 primitive elements, according to what we know. If you want to find the number of elements of order k, it's 5k. So the number of elements of order 12 is 512. And in fact, all of them are given, so other primitive 12 equal to 1. i.e. 2 to the power 1, 2 to the power 2, 2, 3, 4, 5. 5, 2 to the power 7, 8, 9, 10, 11, 11. Okay, we compute those. Well, 2 to the power 5 is this thing times 2, so it is 6. 2 to the power 7 is this times this, so it's 24, which is -2. 2 to the power 11 is the same as 1/2. Just because 2 to the power 12 is already 1, so this is 1 divided by 2. What is 1 divided by 2 modulo 13? 7, yes. So this is a number which you, if after you multiply it by 2, you get 1, so it must be 7. Okay, so here are all the roots, all the primitive roots. 2, 6, minus 2, 7. Okay, maybe we can do them something kind of useful. Well, yes, let's try solutions of x cubed equivalent to 1 modulo 13. How can we solve such an equation? 7. Okay, so if you take, okay, so 2 to the power 11 times 2 is already 2 to the power 12, which is 1, right? So I should find some number such that after I multiply it by 2, I get 1 modulo 13. Well, I take 14 divided by 2, I get 7. Okay, so let me try to solve this equation. First of all, well, we've seen such equations, but usually we restricted ourselves to the case when this power was relatively prime to 5 of the modulus. In this case, 5 of the modulus is 12, and 3 is not relatively prime to 12. But now, once we have a primitive root, we can treat such things, well, much easier. I mean, I know that x must be some power of 2, because, well, every number is some power of 2. At least modulo 13. So, x is 2 to some power alpha. What can you say about this alpha? Well, 2 to the power 3 alpha is equal to 1 modulo 13. Yes, this means that 3 alpha is divisible by 12. That's exactly the same statement, because order of 2 is exactly 12. If you know that 2 to some power is equal to 1, it means that this power is divisible by 12. So it means that 3 alpha is divisible by 12. It means that alpha is divisible by 4. So here are all the solutions. X is 2 to the power 0, 2 to the power 4, 2 to the power 8. That's it. Well, we can actually compute those. 2 to the power 4 is 16. So it's 1. 2 to the power 4 is 16, so it's 3. And 2 to the power 8 is 9. Here are all the solutions. Well, of course, it's not a free way to get those solutions. You have to compute to find some primitive element modulo 13. But once you do have a primitive element, solving such equations is extremely easy. In fact, solving any kind of equation which is of the kind something times f to some power is something else code becomes quite easy.
Wait, how do you know actually because we put the power out how much?
So this is, okay, so this is of course in the sense of modulo 13. And well, sometimes I forget saying that I am working modulo 13, but every element which is not equal to 0 is a power of 2 modulo 13. That's the meaning of saying that 2 is a primitive element. Because well, all the powers of 2, so from 2 to the power 0 to 2 to the power 12,
Yeah.
11 are different elements. There are 12 of them. So this set covers all possibilities.
Yeah.
Okay? So every element is a power of 2. Okay. It's not divisible, it's divisible. Yes. 0 is not divisible by any number. And 1 is definitely divisible. Always. So maybe I'm not familiar with this presentation, which will like this. Okay, so next time we'll see many more applications of this primitive group theory. See you next time.